Hello, good morning everyone. Let's start today's session. So today we are going to focus upon the concept of curse of dimensionality. Curse of dimensionality. Initially, we'll talk about this concept in relation with the algorithm that we have studied recently, that is the KNN algorithm or the nearest neighbor algorithm, and then we'll try to extend this concept in general. So, to begin with, let us understand what this term means, curse of dimensionality. In fact, whenever we are dealing with machine learning algorithms, we need to have the data, lots of data. And this data actually comprises of the instances or the examples. And every instance or example is described by the set of features. Right? So while dealing with any machine learning algorithm, we need to make use of data sets or huge data. That data actually comprises of the samples or the instances or the examples, and these instances are being described with the set of features. Now, let us imagine that instances are described by 20 features. Let us assume that the instances are described by 20 features. But only 3 features out of those 20 are relevant to the target function that we are describing or that we are coming up. So, if out of 20 features, only 3 features are relevant, then remaining 17 features may adversely impact our target function or our result. And this is what the problem of curse of dimensionality. So, nearest neighbor algorithm is easily misled when instance space is high dimensional and dominated by large number of irrelevant features. So what are irrelevant features? The features those actually do not contribute into the prediction. The instances are being described with lots of features, but there are many features which are not actually useful. And if we are having such irrelevant features in our feature vectors, then it may adversely impact the performance of the nearest neighbor algorithm. So this is in view of nearest neighbor algorithm, this is what we mean by curse of dimensionality. Error increases with the increase in the number of features. So if, say for example, if I am having 10 features or 50 features or 100 features, as I go on increasing the number of features, sometimes it may happen that my performance decreases. So increase in number of features may result in decrease in the performance of the algorithm. A higher number of dimensions actually theoretically allow more information to be stored. But if practically we look at it, it rarely helps due to the higher possibility of noise and the redundant data that is available in real world scenarios. What we mean by that? Suppose I'm talking about one example wherein I'm having the instances, say x1, x2 are the instances up to xm, and every instance is being described with the features. So I'm having first feature of first instance, second feature of first instance, and so on. And this is how I am having the nth feature of first instance. Similarly, every instance is being described with n number of features. Right? Now, n number of features means our feature space is n dimensional. Right? If I am having n number of features, my feature space is n dimensional. Okay? And typically or theoretically, we may feel that if I am having many number of features, obviously I am describing my instance with more details. So with more number of features, theoretically, we feel that we are storing more information, right? And we may feel that this more information may contribute in improvement of the performance of our model. But in fact, if practically we look at this problem, increase in number of features rarely helps. And the reason is, if we are having lots of features, then it may happen that few of the features are redundant. So, even though we feel that if we are having lots of features, we are storing more and more information, and that might be helpful so that we can improve the performance of our model, because we are storing lots of information about the instances. But practically, it really helps, because if we are having lots of features, then there are more possibilities that we are storing some noisy data, or we are storing some redundant data, repeated data that is not actually contributing to improve the performance of our model, right? And this is what the problem of curse of dimensionality. Actually, this term curse of dimensionality is being introduced R. Bellman, who was a mathematician, and in his book of dynamic programming, he has introduced this term curse of dimensionality. And according to him, the curse of dimensionality is the problem that is caused by exponential increase in volume associated with adding extra dimension into the Euclidean space. So, if we are having the Euclidean space with n dimensions, then he observed that if we go on adding the dimensions to the Euclidean space, the problem is created by the exponential increase in volume associated with this increase in dimensionality. So the curse of dimensionality basically means that the error increases with the increase in number of features. I'll repeat, the curse of dimensionality means that the error increases with increase of features, and it refers to the fact that the algorithms are harder to design in high dimensions, and often they require exponentially high running time to execute those algorithms. So even though a higher number of dimensions theoretically allow more information to be stored, practically it rarely helps due to the higher size and redundancy in the data. So in machine learning, a small increase in dimensionality would require large increase in the volume of the data set to maintain the similar level of performance of the algorithm. I'll repeat, in machine learning, if we add dimensionality, that means if we add the number of features, then it is important to increase the volume of data also for training in order to maintain the similar level of performance. Right? So let us see with a diagrammatic representation what we mean by that. So see here, we are assuming that the number of training examples is fixed throughout the experimentation. So this is a plot of a typical experiment that is performed. So when performing this experiment, what we have done is the number of training examples are fixed throughout the experimentation. So if, say for example, if I am having the number of training examples, say 500, then these training examples are kept fixed, right? And what has been done is the number of features are being added, right? So see here, in every experiment the number of features are being added. So on x-axis we are having dimensionality or the number of features, and with respect to the number of features with this fixed size of training data set, we have evaluated the performance of our classifier, and we have plotted this classifier performance against the dimensionality or the number of features. So if we look at this particular plot, what we observe, as the dimensionality increases, the classifier's performance increases until the optimal number of features is reached. After that, if we go on increasing the number of features or dimensionality without increasing the number of training samples, this may result in decrease in the classifier performance. Please look at this. This is the degradation of the classification performance, right? And this is due to the curse of dimensionality. Okay, so please once again try to understand the concept. This is very important concept that we are discussing, and afterwards we are going to find out the solutions for this problem. So what is curse of dimensionality? In fact, theoretically, what we are expecting is if the instances in my training data set, if the instances in my training data set are described with many features, then theoretically what we understand is we are storing more information about the instance, right? So this is theoretical understanding. If we are describing the instances with many number of features, then theoretically we may say that we are storing more information. But practically speaking, this information rarely helps us to improve the performance of our classifier or performance of our model. Why? Because if we are having lots of features and if we are not having many number of training examples in that proportion, then what will happen is by increasing the number of features, we are increasing the noise or we are increasing the redundant data that is being used to describe the instances. And that is why even though we add into the dimensionality, we add the number of features, those describe the instances, those may not help us practically to improve the performance. And that is why I am illustrating one experimental result so that you can understand this concept clearly. So what we have done here is we have kept the number of training examples fixed throughout the experimentation. Say for example, the number of training examples are 500. Okay, and what we have done is, let us assume that for experiments, the first experiment is performed with 500 samples, right, and 10 features. So number of features are 10. Then we are having the same 500 examples, but we have added few features. And now the experimentation is carried out with 20 features. Suppose we go on increasing the number of features, say 10, 20, 30, 40 and so on. Right? The number of training examples remains same. Then what we have done is, see here, on x-axis we have plotted the dimensionality, that is the number of features. So say for example, this is for number of features 10, this is for number of features 20, 30, 40 and so on. Let us assume. Okay. So what will happen is, at every or for every number of instances, for every experiment, we have computed the performance of classifier. Right? The performance of classifier. So what is the accuracy or what is the error that is being produced by our classifier with say 10 number of features, say 20 number of features, then 30 number of features and so on. So the observation is, as the dimensionality increases, the classifier's performance increases until the optimal number of features. Say for example, in this particular case, at this instance, we are getting the highest performance. So the number of features, say for example, are 20. So for 20 number of features, we are getting the optimal or we are getting the maximum performance of our classifier. Right? So the performance of the classifier goes on increasing till the number of features are reached to some optimal value. Here in this case it is 20. Let us assume. But further, if we go on increasing the number of features, then what has happened? The performance has started degradation. So performance is degraded after the number of features 20. Right? We have kept the number of training examples fixed. Right? So for fixed number of training examples, if we go on increasing the number of features, after it reaches to some optimal number of features, my classifier performance goes on decreasing. So there is no value addition of adding the number of features. Right? And this problem is known as curse of dimensionality. Are you able to understand?
Yes, ma'am.
Fine. So, further, I would like to referring to if what actually is happening if we are having too many features. We have seen this concept earlier also. If we are having too many features, then it results in overfitting. Right? In case of limited number of training examples. I'll repeat. If I am having too many features, then my model overfits. If I am having limited number of training examples in my data set. Why it happens? Because my model tries to learn the exceptions also, or the noisy data also, that are not specific to the training data. Some noise might be there, and such exceptions are also being learned, and the model will not generalize well, right, when the new data or new test samples are encountered. In other words, if the amount of available training data is fixed, then overfitting occurs if we keep on adding the dimensions. If we keep adding the dimensions, the amount of training data should also grow exponentially fast to maintain the same coverage and to avoid the overfitting. So if we are adding the dimensions, then obviously what we need to do? If we are adding the dimensions, we need to add training examples also. If we are adding dimensions, if we are adding the number of features, but if we are not having that much training examples available, then it results in overfitting and degradation of performance. Please once again understand the problem. If we are adding number of features, then it may result in overfitting. If we are having limited training examples, if we want to add the dimensionality, if we want to add the number of features, then in that proportion we should increase the training data as well to keep the performance intact. Otherwise, the model will overfit and we will see the degradation in our performance of the model. Right? So, I hope now you must have understood what is the problem of curse of dimensionality. If we want to overcome the curse of dimensionality problem, then what to do? So, in fact, we are going to extend this concept in general, but let us first talk about the overcoming of this problem with respect to the k nearest neighbor algorithm. So if we want to overcome this curse of dimensionality problem with respect to KNN algorithm, then what to do? We are having two approaches. First approach is we should weigh each attribute differently when calculating the distance between two instances. So we know actually how KNN algorithm works. In this k nearest neighbor algorithm, what we do? We are having the instance space, right? Wherein we are having the samples. Right? And whenever the test sample comes in, so whenever the test sample comes in, what we do? We try to find k nearest neighbors. So k neighbors are being identified. So for this particular test sample, we try to find out if k equal to 3. Then what we do? We try to find out 3 nearest neighbors. Right? So let us say that we are having this first neighbor, this is the second neighbor, and this is the third neighbor. So how we are identifying these neighbors? We are trying to find out the distance between the test query sample and the neighbors. So we have seen this, right? So every instance, every neighbor is described with a feature vector. Right? So this every instance is being described with a feature vector. So if we want to overcome this curse of dimensionality in KNN, then what we can do is we can weigh each attribute differently when computing the distance between two instances. Here, for example, we have seen that how to compute this distance between two instances. We have made use of the Euclidean distance. Right? And if we are computing the Euclidean distance, this Euclidean distance is being computed by considering the features of the instances. So what we are trying to do is, if we want to overcome this curse of dimensionality problem, then we should provide some weights to the different attributes. So if I am having features, say 10 features if I am having, then every feature may have some different weight. And based on that weight, the distance between two instances is being computed. Right? Also, we are using the cross-validation approach. So, what we are going to do is, we are going to select a random subset of available data to use as training examples, and then we are going to determine the weights like Z1, Z2 up to Zn as the weights for n attributes. Right? So, suppose I am having say feature 1, feature 2, feature 3 and so on up to feature n. Then what I am going to do is, I am going to associate with every feature some weight. So Z1 is the weight associated with F1. Z2 is the weight associated with F2. Z3 is the weight associated with F3 and so on. Right? So we are going to determine this value associated with determine these values such that our error is minimum. So obviously, by making use of this scheme, what we are trying to do is, we are trying to find out which feature is more important. Right? So by adjusting those values of the weights, right, we are giving certain importance to every feature. If the weight associated is more, that means that feature is more important. If the weight associated is small, then this means that particular feature is less important. Right? So we go on changing these values of weights and we try to find out the error. Right? And we are going to repeat this process multiple times to have more accurate estimate of these weighing factors. Right? And whenever we get the maximum performance or the minimum error, then we will stop iterating. And this may help us to suppress the impact of irrelevant attributes. Why? Because if the attribute or the feature is irrelevant, we are providing some smaller weight to that feature. So this is approach number 1 to overcome the curse of dimensionality with respect to this KNN algorithm. Fine. So let me proceed with approach number 2 now to overcome this curse of dimensionality. And please remember, we are right now talking about only the KNN algorithm or nearest neighbor algorithm. And afterwards, we are going to extend this concept further. So this approach number 2. In approach number 2, what we are going to do is, we are going to completely eliminate the least relevant attributes or features. Completely eliminate or discard the least relevant attributes or features. Meaning, it is equivalent to setting this weight Zi associated with feature Fi to 0. That means we are eliminating the effect of that feature. Are you getting me? Yes?
No, ma'am.
Yes.
See, what we are trying to do in the approach number 1, we had several features and associated weights. Right? And what we were trying to do, we were trying to find out the appropriate weights for the features so that error gets reduced. Right? This was the approach number 1. Fine. So what we did earlier, we were having different weights associated with different features, and through experimentation we identified that which feature is most appropriate. For that feature we were providing higher weight, and whichever is the feature that is not relevant, we are providing the least weight to that feature. Right? Now, in this approach 2, what actually we are doing is, instead of providing the least weight to that particular feature, it may happen that we can completely eliminate these least relevant attributes or features. Meaning, if we associate, say, 0 weight with this F2, then what will happen? This feature will be eliminated from my feature vector. Right? So I'll not be considering this feature at all. So obviously, if I'm not considering this feature, that means I'm reducing the dimensionality. Right? So whichever are the features, those are most relevant for me, I'll be keeping only those features, and I'm going to completely eliminate least relevant attributes or features by putting the weight as 0 for that attribute or the feature. Got it?
Yes, ma'am.
Fine. So this is approach number 2. In fact, this method was proposed by 2 researchers, Murray and Lee, in 1994 for selecting the relevant subsets of the attributes for KNN algorithm. Right? So these are the possible ways those we may use to overcome this curse of dimensionality problem with respect to KNN algorithm. Now, when to consider the nearest neighbor algorithms? So when we should go for these kinds of nearest neighbors algorithms, right? So we have listed here few important points, those we should consider while using this nearest neighbor algorithm for classification or regression, right? Obviously, our instances are being described in n-dimensional space. So we are having n features, n may be anything depending on our problem statement, right? If we are having less number of features or attributes, right? And typically, if our features are normalized, We have seen this concept of feature normalization earlier, right? So if we are having less number of features, and typically if the features are normalized, then we may think of using this nearest neighbor algorithm. Also, if we are having lots of training data, then also we should think of this nearest neighbor algorithm. The advantages of nearest neighbor algorithm are training is very fast. In fact, we are not having any kind of training. In our training phase of nearest neighbor algorithm, simply we are storing the samples. Right? So we are not at all manipulating in training phase. So training phase is very fast. Simply we are storing the instances. Right? This KNN algorithm or the nearest neighbor algorithms may help us learn the complex target functions. So in case of testing, we simply try to find out the distances, and based on those distances, it is possible for us to predict. Right? So it is very helpful if we want to learn the complex target functions. And in these algorithms, there is no chance of losing any information. So these are the advantages with respect to the nearest neighbor algorithms. But there are certain disadvantages also. And what are those disadvantages? These algorithms are very slow at query time. We have seen this earlier. So what we mean by that? Slow at query time. As I said, in training, we are simply storing the instances. And in case of prediction phase, whichever are the number of instances that we have, right, spread in the space, feature space, at query time, we need to find out the distance of the query instance with each and every training example. So computation is much more, right, at the time of querying or at the time of testing, and it as the time required to compute all those distances and to come up with k neighbors, right, as this time is much more, our algorithm becomes slow at query time. To overcome this disadvantage, there are some strategies those can be used, like pre-sorting and indexing the training samples. So we may make use of certain data structures like KD trees, one kind of tree, or some search trees. Those may reduce this time of searching, right? But still, the disadvantage is the nearest neighbor algorithms work very slow at query time, right? And the most or the another disadvantage that we should avoid is sometimes if we are having irrelevant features in our data set describing the instances, then the nearest neighbor algorithms are easily fooled by these irrelevant features. So irrelevant features are adding some irrelevant information, and this irrelevant information actually misled these nearest neighbor algorithms to come up with the more accurate results, and that is the second disadvantage of these kinds of algorithms. As I stated earlier, to deal with this second disadvantage, having irrelevant features, we have seen two approaches those can be used, right? So we may weigh different attributes with different weights, or even we may eliminate the irrelevant features. And by making minimum number of features, or by having minimum number of features describing the instance, it is possible to overcome this disadvantage and to come up with good results. Right? So this is what we need to consider whenever we are thinking of making use of nearest neighbors algorithm. Right? So far we have seen two nearest neighbor algorithms. The first is K nearest neighbor algorithm, and the second was the distance weighted nearest neighbor algorithm. Right? So while selecting those algorithms, we should keep all those points in mind. So if we are having less number of features, right, and if the features are typically normalized, and if we are having enough number of training data available with us, then we may go with this nearest neighbor algorithm. Right? Is there any difficulty? Is there any doubt? If you have any doubts, please let me know.
Ma'am,
Yes.
KNN is mostly used for classification. So if we want to apply like for regression problem, then how can we do?
No. K nearest neighbor algorithm is used for both classification as well as regression. In classification, what happens, as I stated earlier, the nearest K neighbors, right, will vote for the class. Right? So majority
Yes,
of
ma'am.
K samples, if whichever class they have, that class is being predicted for the query sample. In case of regression, what happens is, if I have identified K nearest neighbors, then obviously the Y value for these K nearest neighbors is a number, a real number. So in case of regression, the YQ value is predicted as the mean of all those real numbers. So if, say for example, if I am having K equal to 5, so I'll be having 5 YI values associated with these 5 neighbors. Right? And these are actually the numbers. So if it is say 10.5, 11, then 12, 9.5 and say 3.5, something like that. Then what will happen is, if these are 5 nearest neighbors, then the mean of all those YIs is being computed, and that mean becomes my YQ. So KNN algorithm can also be used for regression.
Okay, ma'am.
Right? So
Yes.
both the predictions are possible, classification as well as regression. Right?
Yes, ma'am.
Is there any doubt?
No, ma'am.
Fine. So let's conclude today's session. In the next session, we are going to extend this concept of curse of dimensionality in general, and we'll be focusing upon the algorithms like feature selection algorithms and feature extraction algorithms. Right? So we are looking at these kinds of algorithms in the next session. So let's conclude today. Thank you.